So good afternoon. We will continue our discussion on the physics of molecules. We analyzed it in detail. The simplest problem in molecule, namely, is a pseudo molecule, is called H2 plus molecular ion. In that case, we can really form the LCAO using the 1s atomic states from the two nuclei, and therefore we can build up a 2x2 matrix and do the whole calculation. But the physics is very simple. So you have a 1s on one side, another 1s on the other side. When they come closer to a reasonable distance, namely in the quantum mechanical distance, 1 angstrom or 2, then they will start to influence each other. In particular, it is the off-diagonal elements, that is to say, 1s on the left, 1s on the right, and the Hamiltonian in the middle. That energy plays the role of pushing the two atomic energies up and down. If the electrons only feel the pushed down molecular orbital, so-called MO, then some energy will be gained. And therefore, this combination called molecule will be more stable than two neutral atoms far apart. And that is the idea behind why two things bind in physics. So today we will carry this idea through to discuss more molecules, but we will not do anything very quantitative. But we have these big ideas, very quantum mechanical ideas in our mind, so that we will carry this idea and see how far we can go in explaining the physics of many different molecules. So let me see. So it is 12:32. I have 18 students out of 55. So welcome you all. There are two who are just sitting in. Thank you for coming. So here, last time we ended on this page, it is about hydrogen molecule. So it's not H2 plus, we have 2 electrons, 2 centers. It is a more complicated problem, and fortunately or unfortunately, there's no analytic solution, no matter how strong your mathematical skills may be. That's nice. Nonetheless, it's the same thing. So you have a 1s from the left hydrogen atom, 1s from the right hydrogen atom. You form the LCAO. The complexity of the H2 problem comes from the electron-electron Coulomb repulsion. So we have encountered it in helium atom. So you can imagine either you buy a package, you pick some self-consistent Hartree method to do the calculation, and then after that, you get the molecular orbitals, and then you only have 2 electrons to fill in. Naturally, some energy will be gained, and therefore H2 exists. And then you might have learned in your chemistry course before, there are things called single bond, double bond, triple bond, something like that. So here we can define so-called bond order within quantum mechanics and LCAO. It is a proper definition. So H2, as you know, it has a single bond and is covalent in character because the electrons tend to spend some probability, appreciate probability in the middle between 2 nuclei. So the first concept today is to define what is called the bond order. If it is 1, it is called single bond. If it is 2, it is called double bond. It could be 0.5, then you have half a bond. So what does it mean by bond order? The definition is as follows. After you fill in the electrons, you count how many electrons are there in the bonding orbitals. Then you count how many electrons are in the antibonding orbitals, you take the difference and then divide it by 2. This divided by 2 because a bond will be shared between 2 atoms. Okay, so let's count hydrogen. So you have 2 electrons in the lowest. This is a bonding molecular orbitals. This will be antibonding. This will be bonding from 2s, is empty anyway. This is antibonding from 2s. So therefore, for hydrogen molecule, we have 2 electrons in bonding, none in antibonding. So the numerator is 2 divided by 2, you get 1, you call it single bond. Now from this point on, you don't need to memorize things. It is a quantum mechanical concept. And rather interestingly, it is a concept or a definition built upon LCAOMO. Well, LCAOMO is an approximation, but it's a very good approximation. So you have an idea in chemistry about bond, single, triple, double, being defined under some approximation. Interesting thing. Now, how about H2 plus? When you have only 1 electron. Therefore, you have 1 in bonding, none in antibonding divided by 2. So formally speaking, H2 plus is only half a bond. No doubt, the binding energy of H2 plus is smaller than H2. Therefore, it's natural if you have many more electrons in bonding than antibonding, the difference may be 4 divided by 2, that will be double bond, and then you might have triple bond. So that happens, for example, in nitrogen, N2, using the P states. And therefore, that leads us to discuss, so far we have been discussing S state from hydrogen on the left, S state from hydrogen on the right, and then they form linear combination. We haven't talked about P orbitals from the atoms. So here it is the section about PP sigma. So you know what it means, I think. I have a P on the left. Now I have 2 nuclei. There's a special direction. You can call it Z or X or Y, doesn't matter. There is a special direction. That is the key point. So once you have a special direction, you give it a name, say it is Z, then you have a PZ from the right, PZ from the left. They start to come together. Okay, if they come together with the sign of the wave function plus loop, minus loop, plus loop, minus loop, they add together. In the middle, there will be an enhanced probability of finding the electron. That will be a PP sigma. In other way, if it is plus minus pointing at each other, if you add them together, that is to say you minus the 2 things, then you will have a antibonding, a PP sigma star. Okay, so very simple. But before drawing pictures, I would like just to remind you what you learned in the last term for hydrogen. In hydrogen, you have spherically symmetrical potentials. Even in other atoms, we approximate it to be this case. Therefore, the wave function has an angular part, YLM theta phi. And then for P state, it means L is 1. Therefore, you have 1, 0, 1, 1, 1 minus 1. You look up 1, 0, it is cosine theta. Cosine theta means if you have a radial distance 1 times cosine theta is the Z projection. Therefore, this Y10 is naturally pointing at Z. We call it PZ. Okay, I think you have that in your last course. But if you look at 1, 1 and 1 minus 1, they are complex for the reason that you have E I phi and E minus I phi. But chemistry or chemists, well, physicists as well, we want to think in terms of real functions. Well, you can form two linear combinations to make real functions. For example, add them together, you will get sine theta cosine phi. Spherical coordinates, this thing points at x. Therefore, this is px. So it is this same shape, but now pointing at x, the dumbbell, okay? Similarly, if you subtract them together and multiply by an I, then this thing is real. Sine theta sine phi, it points at y. Therefore, summary, L equals 1 is called p orbitals in atomic physics, and you will have px, py, pz, a dumbbell or number 8, something like a number 8, okay, and then point at x, y, z. And if it is a lonely atom, it has no sense about what is a direction. Well, all direction looks the same if it is a lonely atom in the universe. But we are talking about molecules. Once you have a laboring atom coming in, there is a special direction. And that direction, whatever you call it, is special. Therefore, you may call it X, then some stronger bond will be formed along this axis, and the rest you will have pi bond, and that will be pp pi. So that is the big picture. Let's move on. Here is a reminder, because I didn't teach the first course, I just want to make sure that we have the same footing, everybody, okay? So I want to remind you of the pictorial representation of some atomic orbitals. There are different ways. If you read different books, there are different ways to display the hydrogen atomic orbitals. For example, the easier way is just to display the angular dependence. What I mentioned about cosine theta, sine theta, cosine theta, psi phi, cosine theta, sine theta, psi phi. So in that way, you will see the p orbitals like px here, py here, and pz here. And the plus minus here is the sign of the wave function. For example, think about cosine theta. This is a spherical coordinate. Therefore, the theta is count from the z direction. So when you have theta equals 0, it is plus 1. So it is this longest distance from 0, 0, 0 up to here if you are plotting a polar plot. Maybe you can use Mathematica to do polar plots. Now, if you haven't encountered polar plots, then pay attention. I will tell you how to make a polar plot now. So you fix an angle. So theta equals 0, cosine theta is 1. Then you start from 0, 0, 0, the origin, make a dot here that is length 1. All right. Now, cosine 45 degree, it is smaller. Then from the 0, 0, 0, you make a line of that length, shorter length, and then stop there. Okay. Now, theta equals 90 degree is 0. Therefore, it goes to the origin, 0. Now, if you go to 120 degree, it starts to grow again, but there's a sign. It is minus. Okay. Therefore, you see this plus minus label in the p orbital pictures. Do you understand? Okay. Now, this sign is not just mathematics. It's turned out that you can see it and then, add them. They enhance each other because plus means plus. You add them, they don't cancel. And that it will be enhancing the electronic probability there. Okay, do you understand? This is called polar plots. If you understand this, I encourage you to try one of this at home. Once upon a time, there's some graph paper called polar plot graph paper. But of course, your generation may not have seen any graph paper at all, right? You could go to Excel and then you have this fancy plots. It is a, well, advancement, of course. So this is called polar plots. It carries angular information only. But there are other plots that are just as useful and contain a little bit more information. In some way, plotting the S or P orbitals, we also want to carry the radial wave function information. The previous polar plots only contain the YLM theta phi, the theta phi information. So if you have a 2pz, in full term, it is the 210 wave function of hydrogen atom. I look it up, normalization doesn't matter, then you have a radial part. Now, here is the radial information that is missing in the polar plot. And this part is our, like two balls touching, okay? The PZ figure, so this thing, okay? So what if we want to indicate some information including the radial wave function? There are different ways to do it. One is called probability density plots. What are we doing? Now, you take this, you calculate this thing square. So you pick somewhere in space, give it a tiny box, a cube, so you have a volume. You calculate this thing at that r theta phi, then you know what is the number there. It is the probability of finding the electron in this tiny box. This box is located at r theta phi, all right, in spherical coordinates. Depending on the number there, then you decide that number, how many dots you put there, or else how dark you use the color there. Okay, you can use different colors. Darker means a bigger number and so on. Okay, so here is 2pz and 3pz. What I want to show you is that in the previous port, as long as it is pz, it looks the same. It doesn't matter it is 2pz n equals 2 or 3pz n equals 3. However, if you care about more information, you plot 2pz and 3pz, they look slightly different. In a big picture way, they look more or less the same, but you see this lowering of probability, string down, there's a very white region here, meaning very little probability, and then farther away, you have probability again. Okay, that is the note in the 3s wave function, in the radial wave function. Okay, another way to plot this thing, it is called contour plots. It's called probability contour plots. What does it mean? Here, again, it is 2pz, 3pz. All this contour is meant to enclose a certain probability of finding the electron within the region of the contour. It encloses a region, all right? So the smaller contour will be 10%, 20%, and so on. So the bigger one will be 90%. 90%, that is the region, that 90% probability the electron resides inside, okay? So both ways, you see, if you do that, you have more details about the atomic wave function. Even for the S state, if you only care about Y00, that is S state, right? It is a constant, therefore it's like a ball, no directional dependence, okay? However, if you care about the radial information, 1s is slightly different than 2s, slightly different than 3s, as depicted here. Density plot and contour plot. Obviously, this kind of plots, including the radial wave function, also indicate that 3s is extended farther away than 1s. Now that is important in forming bonds, right? In an atom, sodium, say, it is using the 3s electron to form bonds, then there are 1s electrons in sodium as well. But we know that they are not going to affect much because 1s electrons can only live inside this volume. Therefore, its wave function is not going to overlap with the neighboring atom much. Therefore, the overlap or hopping will be small. They don't take part in the chemistry. It is the 3s that take part in the chemistry, okay? So the previous 3 pages are meant to be a reminder. So now we have a common footing, I hope. Then we go back to our discussion of more molecules. I mentioned that for a lonely atom in the universe, it has no sense about what is X, Y, Z. That's true. But in discussing molecules, we have 2 things. So we have atom A, we have an atom B. It doesn't matter where it sits. Once there is a label, then there is a special direction. Okay? You may call it whatever you like, doesn't matter, but one direction is special. So now I rotate this so that I can draw it more easily. I can call it X. Therefore, the X direction will have something special that define what is the sigma bond and what is pi bond. Okay. So last time I mentioned that sigma bond means after you do the quantum mechanics, there is electron distribution. Sigma bond means along this line. You rotate it, there's no change in the electron distribution, and that is called sigma bond. Pi bond does not do that. So now we are ready to discuss PP sigma. It is a P from the left atom, a P from the right atom. Of course, it is not hydrogen anymore. Okay. And then if the plus loop and plus loop meet and add them together, the density or contour plot will look something like this. Okay, so you will have probability between the 2 nuclei of finding the electron there. This is called bonding because this off-diagonal element between the PP matrix is not small, they will push one down, bonding PP, and then one will be pushed up, anti-bonding PP sigma. Okay, that is the case when you subtract them, or else you think about it as the plus loop meets the minus loop. Therefore, there is a nodal plan. In the middle, it is 0. All right, so this is PP antibonding or sigma star. Why is sigma? Because in both cases, along this AB axis, you rotate the whole probability contour plot or density plot. It is invariant with this rotation. With PP, we have more interesting thing. It is called pi bonds. The special direction is in Z. I call this AB nuclei direction, the Z direction. So you can think about an X direction. You have a P, go perpendicular to it, but with a finite extent only. And then you have two things. If the positive loops touches, not big, but at least they reinforce each other, then it is a PP bonding, but it's a pi bond. The other case, when plus loop meets minus and minus meets plus down below that, then the cancellation ensure you have a nodal plan in the middle, is 0 in the middle, okay? And then this is a PP pi bond, but it is anti-bonding. It has a higher energy. So it is lower energy, is higher energy. So in our plot last time, the PP sigma, so you have a PZ, when they're far away, they are the same energy. I'm thinking about the same atom. So, and one is pushing down, one is pushing up. This is sigma, this is anti-bonding sigma. Similarly, this is bonding pi, this is anti-bonding sigma pi. I intentionally draw it a little bit smaller pushing than here for the reason that if all the other conditions remain the same, this overlap, this touching is usually smaller. That is to say, the integral left P, Hamiltonian, right P, do the integral, that is a smaller number, that is the off-diagonal term, pushing the energy. Therefore, if we put everything together, I have an atom A and atom B, okay? Now the atom will carry Px, Py, Pz. The Z direction is the direction where the two nuclei lie. So it is a special direction. So the Pz will form sigma bonding and sigma anti-bonding. And then the Px, Py will form PP pi, bonding and anti-bonding. And this is displayed in this highest part of the figure, okay? Now you see there's a label with Px, Py being the same. This is due to symmetry, right? What you call X could be Y, what you call Y could be X, is the same physical situation. So there's some degeneracy that one could predict. In this plot, there are also the bonding, anti-bonding due to 1s and 2s schematically plotted there. It is, of course, something down there, no doubt, because atom A will carry its own 1s, so is atom B. So when the atoms come together, of course, 1s could mix with 1s, 2s could mix with 2s, or else you set up a big matrix. Each atom gives 1s, 2s, and Px, Py, Pz. So you have a 10 by 10 matrix and play with it, and then you get 10 eigenvalue for every separation. And indeed, there are 10 values here, okay? But usually, the core electron stuff, they don't push that much because the wave function is closer to each nuclei. They don't extend that much as the outer electron states. And using this picture, we could discuss homonuclei molecules such as fluorine, F2, oxygen, and nitrogen. Each atom is a separate quantum mechanics problem by itself. So there is no one pattern that serves all atoms, molecules. So as you see, actually, the alignment changes as you go across the periodic table to heavier atoms in the 2p row, forming diatomic molecules. So here are the alignments, and then you pick up how many electrons you have, Pauli exclusion principle, you fill it up. Now, look at the situation of F2. Basically, you have everything filled, and then this one is a pi bonding. This is a pi anti-bonding state. These are bonding states. So you have 6 electrons in bonding, 4 in anti-bonding. You have a net 2 electron in bonding divided by 2, then it is a single bond. And that is what you learned, I hope, previously in chemistry. Fluorine, you have a P, you have another P, because all the other things have been filled up, and therefore they form one up, one down pushing. You have 1 electron here, you have 1 electron there, lonely, looking for pairing, and then this is F2 situation. And this is a single bond. You may wonder why I didn't count this full 1s and full 2s bonding anti-bonding state, because they cancel each other. 2 minus 2, 0, okay? Now, if you go to oxygen, then you will have 6 in bonding and only 2 in anti-bonding. Therefore, it is a double bond. Go to nitrogen, you will have 6 in bonding, none in anti-bonding from the P. Therefore, it's a triple bond. And it predicts the right physics. For example, oxygen does have a magnetic dipole moment. So oxygen is paramagnetism, is paramagnetic. For those who are doing thermal and statistical physics course, I think you should have discussed already, say, a system. Every atom has a particular up, down, or 2-level, you may call it spin, or actually it is 2 up or down magnetic dipole moment. Have you done this? Partition functions, things like that. 2-level systems. Did you do anything like that? 有冇做過啊？ Nobody's taking that, okay? Yeah, that's the Curie's law stuff, right? Okay. Now here again, you make connections. Now you are in the upper level of the curriculum, year 3. So there are many different things you learn from E&M, from quantum mechanics, from thermal physics. Actually, they can connect together. So here, when you consider oxygen, all this are paired up. Okay, we talk about angular momentum in the atomic physics part. So here we have a situation, we fill the electrons according to Pauli exclusion principle and the Hund's rule. That's why we put this in different states and then put them up. Well, you can put it down, according to Hund's rule, okay? So therefore, everything here pair up, they don't contribute to net angular momentum. It is this half plus half, okay, that will contribute a net angular momentum per molecule. Therefore, you have a gas of this thing, each has a magnetic dipole moment. You apply a field, slightly more aligned with the field than opposite to the field. Why opposite? Because you have KT, thermal energy. Try to randomize the system. Randomizing it perhaps may be good. Randomizing it, you have entropy. At finite temperature, you want to minimize the Helmholtz free energy, not only the energy. By energy, of course, you want to align lower energy. However, have some of them anti-aligned, you gain entropy, and energy minus Ts is F. Therefore, there may be a number aligned, some number anti-aligned. The net alignment is the paramagnetic response. Get the physics, guys? Okay. Therefore, at a high temperature, you will have the Curie's law. And that prediction turns out to be right, okay? Here, quantum mechanics, the key point is that is experimentally correct. So I end this part with just an optional remark. For example, you may Google and look for what is the weakest bond. This thing, whether you call it a molecule or not, it is arguable. That's why many people, even they did the experiment, they will call it helium dimer. That is to say, two helium may be attracting each other. So here are some two experimental work. These experimentalists are observing some helium-2 formation, but it's very weak. So this is in chemical physics. I give you the number. The binding energy is per mole, it is 0.01 joule per mole, so very tiny. Well, maybe in physicists units, it is 10 to the minus 7 GeV. So, you know, any temperature, well, reasonable temperature will dissociate this thing. And how long is the bond length that they form? Or, you know, for the experimentalists, they observe two helium tends to stay around each other, but at a long distance, 60 angstrom. So it's a very weak bond. That's why their paper with the title, The Weakest Bond. Here's another one, basically confirming the order of magnitude of the numbers in the previous work. So it is in physical review letters. Then they see, again, helium dimer. Then what they saw is, again, is this ballpark, 10 to the minus 7 GeV binding energy. Therefore, anything higher than a millikelvin, 10 to the minus 3 Kelvin, will have the thermal energy sufficient to break them apart. And the bond length actually is the range that they tend to stay with each other. It is 50 angstrom, so very long and very weak thing, okay? Well, in our LCAO discussion, we don't predict that exists, okay? So what it says in our context, maybe believe what quantum mechanics says, but when you do approximations within quantum mechanics, then we better be cautious about the conclusion. And more recently, there is something interesting in astrochemistry or astrophysics, because in the early days of the universe, after the Big Bang, maybe a few minutes later, you start to have this basic nuclei, protons around. And then maybe after 300,000 years after the Big Bang, then you have atoms formation. So we know that the environment in the early universe is most suitable for forming hydrogen and helium, nuclei and atoms. Therefore, it has been a long journey to look for experimental or observational evidence of helium, hydrogen plus iron out there in the dust, okay? So it was not until 2019 that there are two reports around 2 months or so, one in Nature, another in Science, the top two journals, and they are German groups usually. So they observed. So this thing is about astrophysical detection of this helium, hydrogen, helium hydride ions by observation. This entity was fabricated in the lab almost 100 years ago. So it was not until 3 years ago that we scientists really observed that their existence outside somewhere out there. So here's the other paper in the same year. So they're slightly later than the previous Nature work, but they did a little bit more. They measured the abundance. How many of them are there? Okay, so they observe a region and then try to extrapolate some numbers. How many of them are there? Okay, it's our understanding of the nuclear reactions that could happen in the universe, early universe, is right or not quite right. Because if you use nuclear physics, nuclear HH form something and then so on, how could this thing form? Then each reaction has some reaction rate. Therefore, you can predict some what is the percentage that you should observe around a region. Okay, so this paper get into Science, and then they measure the abundance, and they found some so-called enhanced abundance, signaling that we may need to consider the nuclear reaction again more carefully. So here I just want to point out that we are not doing a historical thing. Actually, molecular physics is still well and alive. Another aspect is that in recent years, many people work on ultra cold molecules, including the lab in Professor Wang Dajun in the basement in our department. So he could control cold atoms, so they're moving very slowly, and control the environment so that rubidium or potassium could come together to form, in a controlled way, to form molecules. That is called ultra cold molecules, a very hot research area. So the next thing we would like to discuss, heteronuclei molecules. It means different. The previous one, oxygen, nitrogen, fluorine, they are homo. nuclei, the same thing come together, okay? Once you have heteronuclei, suddenly you have a lot more compounds to play with. The first thing I would like to illustrate is what the sample question did as well. It is HF. It is hydrogen with fluorine. This is a very toxic thing, okay? But it is used in electronic research laboratories. It is used to clean samples very well, semiconductor things, okay? But it is a very bad thing if you get it on your skin, okay? It will go into your bones and then very quickly dissolve your bones, okay? So very dangerous thing. So it is better to learn it quantum mechanically than using it. So it is a heteronuclei thing. So in a pictorial way, we have Coulombic thing, but one has a smaller nuclei. The nuclear attraction is smaller because fewer positive charges. One has a larger positive charges, therefore it's more attractive, a deeper, steeper 1/r thing. So if you put them together and electrons see something like that, okay? So it is different from HOMO situation. Well, in a 1D analogy, this is a shallower well for A. It is a deeper well for B atom. You put them together, this is the molecular problem, okay? It is a one deeper well, try to form a molecule with a shallower well. If you're given this problem, I think at least you can write down some equation to solve it, try to solve it analytically and then numerically. But without doing it, this is a deeper well, electronize it, spend more time here, therefore more probability on this side than the other, right? So think like a physicist. Then ground state. You try to draw this idea out. So probability higher here on this side, smaller here on this side. So it's tilted to this side, okay? Therefore, if you plot square, it's the same shape. Therefore, there is ionic character. More electron density on the deeper side, on the fluorine side, less probability on the hydrogen side. So you will see the electron looks like it goes to the fluorine side. It forms a plus minus ion, they attract, and therefore you have this HF thing, okay? Now, the next few pages is meant to do quantum mechanics without doing it explicitly. But this is high level thing like an applied physicist. So think about the physical situation. Hydrogen, the electron is in 1s. So the most economic way to do LCAO is just to include hydrogen 1s and not the 2s empty stuff. They are many EVs up, doesn't matter. For fluorine, you count, okay? So fluorine is 9 electrons. So 1p, 1s2, 2s2, 2p5. So 2p5, it means maybe px pair up, py pair up, you have 1 electron left, you call that Z. Okay, that is to say, we call the special direction the Z direction. And therefore, we can only, the simplest thing is to take the 2p Z with 1 electron to form bonding with the 1s hydrogen. So the most economical way to do LCAO is just 2 by 2, okay? So I have from hydrogen 1s, fluorine 2pz, linear combination, this is LCAO. I will form 2 MOs. I need to determine the coefficients. Now, variational calculation comes to mind, such a form, 2 by 2 matrix. Every element is like this. Okay? Don't derive it again. Life is short. You don't have that much time. Right? You need to learn new things. So then you start thinking about what are these elements anyway. 1,1 is about hydrogen side. Of course, the hydrogen 1s will be dominating. The fluorine will see that, but it's still a little bit far away. So let's say this is almost like hydrogen minus 13.6 energy, the atomic energy. Okay, that is always quite 90% right. Similarly, this is just fluorine 2p energy. Done. Then, how about S11 and S22? They are normalized. Hydrogen 1s is normalized itself. Fluorine 2p is normalized itself. It's 1. Nice. So now so far, this is 1, this is 1. Okay, and we know this. The next thing is to argue that S12 in principle is not 0 by definition, but they will not be very big. It is the overlap, only the tail meet in the middle. It's just a tiny number. How about this? Ignore that. That will make life easy. So make them 0. What is left is this crucial thing, H12. H12, we don't know what it is. We need to do the integral, call it an energy, okay? So after all this really high level applied quantum mechanics thinking, it is this problem, okay? Now you have done this problem in homework problem set number 1, 2 by 2 matrix. The situation now is, this is quite different from that. How can I know? Because you knew, you learned atoms previously. This is minus 13.6. This is deeper because fluorine is element number 9. It has +9 charge in the nucleus. It's much more attractive. The atomic orbitals will be closer to the nucleus, go inside, okay? Therefore, the energy will be deeper. I mean lower in energy, but the jargon usually is called deeper. So the situation becomes 1s hydrogen, 2p fluorine. This is hydrogen higher, this is fluorine lower, okay? Once you have this situation and you have off-diagonal term here, you know, just slight pushing. Second order perturbation theory, right? This square divided by the difference. The difference is 5 eV, very big, okay? Therefore, what we expect for the formation MO will be fluorine, hydrogen 1s, 1 is pushed down here. This is bonding MO. This is anti-bonding MO. Follow? Now, an even higher level thinking. This MO is closer in energy to fluorine. Therefore, this wave function has a large part, I mean the coefficient is big, large part coming from fluorine and a tiny part coming from hydrogen 1s. The antibonding one is close to hydrogen. It has a lot of hydrogen 1s, a little bit of fluorine 2p. Okay, do you understand what I'm saying? 嗱，如果你唔明咧，你就要睇返第一個功課啦，我冇辦法啦。Okay, 2 by 2 matrix, you can solve the eigenvector. Okay, what I'm saying is the eigenvector feature. So now you have 2 electrons, one from 1s, one from 2p. Go to the bonding according to the Pauli exclusion principle. Therefore, it gains energy because one electron original coming from here rather high. So now we go down. So pretty nice. And then it is ionic character for the reason that this wave function has a lot of foreign 2p character. That is to say, it is inclined or biased to the foreign side. Now 2 electrons go to that side. It looks as if it is a foreign minus ion. Okay, so it's all quantum mechanics in work. You don't need to remember it is ionic, forming anything like that. Okay, like a general chemistry books. We are at a higher level than that. All right, so these are the exercise I encourage you to try. Okay, try to answer them. Why don't we include 1s foreign into the consideration? How about if we include everything from 1s up to 2p x 2py and so on? What's wrong with that? Will you get the same answer? Okay, so it is almost the same thing. Okay, so let's take a break now, and then I will go over water because it's so important, and then we will go into hybridization. So there's a question coming in. So basically, whether or not the bonding is ionic, covalent, uncomprises H11 and delta. Right. Okay. So basically, if in the diatomic case with the same atom, if you are the electrons, you don't know which side to go, right? You will not bias any side. You follow me? Okay, so therefore you can imagine or you can predict if it is homo nuclei is a lot more covalent character. Get that? So therefore you have in diamond, in silicon, you have that is dominating covalent bonds. Get that? When you have heteronuclei, basically you have different nucleus. Attraction is different. Okay, so therefore the diagonal element will be different, and then the off diagonal element H12, H21 usually plays the role of the perturbation numerator, the delta square, but you have to divide by the difference of the atomic energy. Get that? Therefore, 1MO, the one closer, okay, the MO down there, if it is closer in energy than to one atom than the other, then that will have a lot of wave function character coming from the atom with the nearer in energy. Do you follow me? Okay. Therefore, the electron tends to go to that side, and you have another character. So let's have a short break.